Well, here we've got another molecule, boron trifluoride, another exotic fluorine compound. And we've already done the Lewis-Dot structures for these, so there shouldn't be any question about you finding that this has got 24 valence electrons. It's just that it's unusual to end up having an element with only 3 valence electrons making a compound, a covalent compound. But boron can make some covalent compounds, and when you count the 24 valence electrons, you put in 3 bonds, you give the fluorines their extra 6 electrons, give them an octet, and then the natural thing to do is to end up saying, well, our boron doesn't have an octet, let's grab one of these pairs of electrons and make a very nice double bond to get it its octet. But stop, don't, because there's a couple of things against this. First of all, fluorine is very electronegative. It really grabs onto electrons, and trying to get it to share more than one pair of electrons just doesn't happen. You're never going to double bond fluorine. Another reason for that is that boron and aluminum are exceptions, and they're worth remembering because you'll see them. Boron and fluorine end up having a stable structure with just 3 pairs of electrons. So when you're dealing with a covalent compound for boron and aluminum, all you've got to do is get 3 pairs of electrons and stop. Don't go any further. Don't double bond. You're not going to do that. You're going to just leave it as is with its set. So this would be our Lewis-Dot structure for boron trifluoride. And the next step, of course, would be to figure out that it has 3 shared pairs of electrons, unusual. So its steric number is 3. The next step, and that's what we're dealing with right now, is how do we find the shape of this molecule? They always draw it this way, with 90 degrees between each of the fluorines, but that's just because it's easy to draw. The actual shape is going to depend on the valence shell electron pair repulsion model, where these fluorines, these attached atoms, and their pairs of electrons will repel one another as much as they can, which makes sense. The negative charges repel one another. So you would end up trying to move these 3 fluorines and their electrons as far away as possible. And the shape that you end up getting is this one, the trigonoplanar shape. In this case, we've got Daniel Rosenberg at Harvard University, a lecture demonstrator, showing how electrons repel and the shapes that they make. If you haven't seen the video, it's worth watching on the shapes of molecules, because this is the basis of the valence shell electron pair repulsion model. So in the end, even though on a AP exam or most diagrams they'll show boron trifluoride like this, easy to draw, actually they should be drawing it in the shape of a trigonal sp2 hybrid. So we'd have a shape like this, where we'd have 120 degrees between each one of these fluorines in a plane. And this results in something very interesting. The fluorines, if you remember right, is the most electronegative of all the atoms, all the elements. It is the Tyrannosaurus Rex of electronegativity. Everybody bows down to it and will end up having their electrons ripped off and pulled over, even in a covalent bond. And here we've got boron with a wimpy electronegativity of 2. Theoretically, that difference in electronegativity would make this an ionic bond. We wouldn't even have covalent molecules. But this is a molecular substance. It's got a boiling temperature of only 120 degrees below 0. That's not even close to being ionic. What happens is that this pull of electrons of this fluorine, because it's 120 degrees away from this one and 120 degrees away from this one, symmetrically pull against one another, and the net result is 0. It's if you've got a kid in the middle here and 2 people tugging equally in both directions, this kid's not going to move at all. And in this case, the 120, if we had 3 kids at 120 degrees from one another, again, that center would not end up moving. And we have a non-polar molecule. And again, the evidence is that it has a very, very, very low boiling temperature. So there's our shape for boron trifluoride, and also the consequences of that shape, where even if you have polar bonds, one of the most extreme polar bonds you can, they can't be canceled if you've got a symmetrical molecule. So know your symmetrical molecules and make sure you watch that balloon video. It's worth watching.